Welcome back everyone. In this lecture I am going to actually talk about pigeonhole principle, and then we will see some of its applications. So, let us actually start with stating the principle. So, even though the statement of the principle actually sounds somewhat elementary, and it has many interesting applications in counting problems, especially when you are interested in proving existence theorems. So, let us start with the principle and then I will demonstrate some application of it. Okay, let us say that we have n number of objects and r number of boxes. So, let us say n is given to be the number of objects and r is given to be the number of boxes, and if n objects are distributed among these r boxes, where n is given to be strictly bigger than r. So, then we can actually guarantee that there must exist at least one container, one box with more than one element. Okay. So, the principle says if n objects are distributed among R boxes and where n is greater than R. So, then there exist. So, this is where the existential thing comes. So, there exist at least one box with more than one object in it. Okay. So, the principle is very simple to state, because you have only r boxes, r is smaller than n. So, at least one box should have more than one object. So, that is what it says. So, let us actually make a sharper version of this and then write everything in terms of sets and functions, and that is what going to be useful in applying this pigeonhole principle in most of the places. So, let us formalize it. Let us say we have actually these sets instead of boxes and objects. So, we have n and r are the given sets, where the cardinality of n is given to be n and the cardinality of r is given to be r, and we assume that n is greater than r. That means, the number of objects are more than number of boxes. So, how do we actually formulate everything using sets, because assigning an object to a box, that you can actually treat it like a function. So, basically you have a function from that n number of objects to this r number of boxes, and that is what we are going to actually use. So, that means we have a function that is defined from this n to r. So, then what we can guarantee, because the number of elements in the domain is strictly greater than the number of elements in the range. So, now we can guarantee that at least one element in the range, there exists one element R A in R, such that when we are looking at the pre image of that F inverse of A. So, this pre image, so this is going to have cardinality strictly greater than or equal to 2. So, it is greater than or equal to 2. And one can actually say something more, like, because we have specified how many boxes are there. So, that means the cardinality of this pre-image, one can prove that it should be at least this floor of n minus 1 by r plus 1. So, this we can guarantee. So, this is what our pigeonhole principle actually says. So, let us look at this pictorially. So, we have this function that is defined between n and r, and we have only r number of elements here. So, you have A1, A2 etcetera AR, and then you have some elements here x1 etcetera xn, and then for each element we are looking at the pre-image, how many elements can be there, and we want to guarantee that at least one pre-image, when you are looking at it, it should have at least this number of number of elements, which is 1 plus n minus 1 choose r, sorry, 1 n minus 1 divided by r. Okay. So, that is guaranteed by Pigeonhole principle. Of course, the proof is somewhat simpler, it is not very hard. So, if we assume by contrapositive that there is no such A, then we arrive at contradiction. So, let us look at the proof. So, assume that such a does not exist. Assume that such A in R does not exist. So, that means what? That means whenever you are looking at the cardinality of this pre-image, all of them should be strictly less than this n minus 1 by r plus 1, and this is true for all A in R. So, that is what this statement actually gives. So, the assumption on our set gives us that all the pre-images have cardinality strictly less than this element. So, now so this would immediately imply that so the cardinality of n, which is going to be the sum of the pre-images of all elements. So, look at n. So, this you can write it as disjoint union of F inverse of A comes from R. So, note that F inverse of A intersection F inverse of B, this is supposed to be empty, as if there is an element x here, then what would happen? Then f of x becomes A as well as f of x becomes B. Okay. If A not equal to B coming from R, so then we must have that f inverse of A intersection with f inverse of B is empty. Okay. And this is actually violation of the function definition. Okay. So, this cannot happen. And that would imply that this union f inverse of A in R, it is a disjoint union, and that has to exhaust this entire n. So, this equality we are getting it for free. So, then using this you can see that the cardinality of n is going to be exactly same as the sum of the cardinality of the pre-images for all A in R. So, now with this assumption we can see that each pre-image, it cannot have more than this n minus 1 choose R elements. So, this immediately would imply the cardinality of F inverse of A is less than or equal to n minus 1 divided by R, floor of that. Okay. So, then if we substitute that, then we get exactly this is less than or equal to summation n minus 1 divided by R, floor of that, where A will run over from R. Since there are exactly R number of elements, this immediately implies the cardinality of n is less than or equal to R times n minus 1 divided by R. So, now it is not very difficult to see this number is exactly less than or equal to n minus 1 at most. So, that tells you that the cardinality of n cannot exceed n minus 1, but from our assumption we see that the cardinality of n is exactly smaller. So, that tells us that we arrive at contradiction. So, this is actually a contradiction. So, that proves that our assumption that we made in the beginning, that is wrong. So, that means we get that there exists A in R such that the cardinality of F inverse of A is exactly sorry, is at least n minus 1 divided by r plus 1. Okay. So, this is always true, and this is very important observation, and this actually can be used in proving many existence results. So, let us actually look at such examples. So, okay. The very first example that I am going to do is what is called the party problem, and it is part of what is called Ramsey theory. Okay. So, the example 1 is the party problem. So, the party problem is actually somewhat well known problem. It is easy to state, and if you think about it, it is a part of this bigger theory called Ramsey theory, which I am not going to get into. And indeed, what we are going to say, the Ramsey number R of 3 comma 3 is what we are interested in. Okay, let me state the party problem, which does not require any mathematical background. One can state this at the level of like common knowledge. So, let me state the problem and then see like what it says. So, it is about a party in any group of 6 people who are attending the party. So, we can guarantee that there are either 3 people who all know each other, or there are 3 people who are all strangers to each other. So, that is what this party problem actually guarantees. So, let me state it: in any group of 6 people. So, that means you take any party with 6 people. So, there are either 3 people who all know each other, 3 people who all know each other, or 3 people who are all strangers to each other, who are all strangers to each other. Okay, it is some very strange phenomena that is happening. So, if you take a group of 3 people, so you have some 3 members who know each other, all know each other, that is important, and you have 3 set of people, they do not know each other, completely strangers to each other. So, that is what it guarantees. Okay, how one can approach such problem? It is basically an application of Pigeonhole Principle. So, we have to invoke Pigeonhole Principle and then guarantee that you will always have solutions to this party problem. So, let us formulate it properly. So, what we are going to do? We are going to draw like we are going to interpret everything in terms of graphs. So, first what you do, you actually label all the people as vertices, and then you start drawing edges between them, and then you color them with the blue edges if they know each other, and then you color the edges to be like red edges then if they do not know each other. So, let us start doing that, then using that we will be able to actually make an argument. So, what we are going to do? So, label the people as let us say P1 etc. P6, okay, these are all the people, and then we are going to draw edges between any 2 different people. So, that means we have 6 vertices, okay, and then let us call them P1, P2, P3, P4, P5 and P6, and then now what we will do, we just draw edges between any two different people, whether they know or don't know, does not matter. So, now I have to connect this. So, let us start counting. So, this one has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, and then this one should be connected 5. So, each vertex you will have 5 edges going from that. Okay. So, now what we are going to do? We are going to draw either. So, we are going to like label these with edges as blue or red, depending upon whether given those two people, like they are the vertices, they know each other or not. For example, take P1 and P6. So, we label the edge by blue if they know each other. Okay. So, draw blue edge if Pi and Pj know each other. Okay. So, then what we are going to do? We are going to draw actually red edge. So, draw red edge if Pi and Pj do not know each other. Okay. So, this is what we are doing. So, that means I am going to label like red, blue, like that. Okay. This is some random labeling that I am doing. So, if you think about it, my set is going to be is that the set of edges. So, you can collect all the edges and that is going to be my E. So, this is the set of edges and my C. So, that is going to be the colors, either blue or red. So, each edge I have assigned blue or red. So, that is the assignment that we have done here. Okay. So, we have taken an edge and then we have labeled it either blue or red. So, that is the assignment, that is the mapping that we are talking about. So, now if we go back to the promising result, what it says that there are either 3 people who all know each other. So, that means it actually guarantees a triangle with all blue edges. Okay. So, what our result guarantees? Either there exists a triangle with all blue edges. Okay. That means the people in that triangle, okay, like some Pi, Pj and Pk. So, they all have these blue edges and that means they all know each other. So, that means the people who are the vertices in that triangle, so they know each other. And similarly, either this happens or we can guarantee that there exists a triangle that contains only red edges. So, that means the people in that triangle, they do not know each other. The people in that triangle, they are strangers to each other, they do not know each other. And this is what we need to actually guarantee. Okay, how we are going to guarantee? So, since there are 5 edges coming from each vertex, that is what we are going to use. So, let us say we start with P1. Since there are 5 edges coming from P1 and only 2 colors are used, which are blue or red. So, we can guarantee that we must have uh, 3 people. Okay. Without loss of generality, we can label them P2, P3, P4. So, having same colorage. So, what we are going to do? We are going to look at this P1. So, from P1 we have this 5 edges coming out 1, 2, 3, 4, 5. So, all of them are actually labeled either blue or red. So, now we can guarantee that it should have 3 edges having same color. So, that how do we actually guarantee? So, you have this function which is function from the edges to the color C. Now, you can restrict this function only the edges actually comes out of this P1. So, the function you can restrict to edges from P1, which is exactly 5 edges, and then you have the colors which is has exactly 2 colors. So, this guarantees that there is at least one color whose pre-image will have at least 3 members. Okay. So, this is exactly what we have proved before. So, one pre-image will have at least n minus 1 divided by r. So, which is exactly 5 minus 1 divided by r, which is 2. So, plus 1. So, which is exactly 2 plus 1, which is 3. So, at least one pre-image must have 3 elements. So, we can use this argument and then say that so without loss of generality, we relabel them so that we can call them as P2, P3 and P4. Okay. So, these people, okay, with P1 between P1 and these people, okay, P2, P3 and P4, they all have same color, these edges, okay, the edges from this P1, P2, P3 and P1 have same color. Okay. So, we can call that as blue without loss of generality. Okay. Say that color is blue. So, let us say this is blue, blue, blue. Okay. So, now what we are going to do? We are going to just look at the edges between these two. Okay. If the edge between P2, P3 that is blue, then we are done. Okay. Let us say, so P2, P3 if has blue edge, then we are done, because this P1, P2 and P3. So, this will make a triangle with blue edges. So, then we are done. Similarly, if we have edge between P3 and P4 which is blue. So, if we have blue between P3 and P4, again we are done. Okay. So, that means we can assume that so this is red and this is again red. Okay. Now, look at this P 2 P 4. So, this P 2 P 4 again it is connected, P 2 P 4 is connected. If this is blue, if this is blue, okay, so I am going to draw it here. So, if this is going to be blue, again we are done, because we have this P 1, P 2 and P 4. This is blue, this is blue. So, if this is blue, so then we are done. Okay. So, then for same reason we are done. Okay. Otherwise, what is it going to have? Otherwise, it is going to have indeed red between it, P 2 and P 4. Okay. So, we are not going to have blue here. So, we will be having red here. So, if we have this red, so then you can look at this P 2, P 3, P 4, P 2, P 3 and P 4. So, this we have assumed it to be red, this we have assumed it to be red, and this P 2 P 4 again we have red. So, this makes triangle with red edges. Okay. It is basically existence proof. It actually guarantees that when you have a graph which is the complete graph on this 6 vertices, and if you actually color with only 2 colors, blue and red, of all edges of this complete graph, then what we have indeed proved, we proved that either there exists a triangle with all blue edges, or there exists a triangle with all red edges. So, they all will have like same color edges, that is what we have proved. Okay. And this proof indeed uses this pigeonhole principle very implicitly, that which I have made it very explicit. Basically, the argument is here is what used. If you take the edges that are actually coming from P 1 and then you look at the colors that are used, since there are 5 edges, at least 3 edges should have same color. So, that is what our pigeonhole principle says, and using that we can guarantee that we have exactly this triangle which has either all edges are blue or all edges are red, which translate back to existence of 3 people who all know each other, or existence of 3 people who are all strangers to each other. So, that is what the actual party problem. Okay. So, like I said, the pigeonhole principle actually, even though it sounds like a very simple statement, this can actually prove some very strong statements in mathematics. For example, this statement, which actually part of this starting point of this Ramsey theory is very powerful. And similarly, one can prove some interesting results in a number theory as well. For that we need to actually kind of develop a little bit of number theory. So, then one can actually formulate some questions about existence of something, and that will be kind of useful. So, one such problem, maybe like one can think about it, let me state the problem. Maybe if I, after developing enough number theory, we will be able to attack this problem. So, let me state it as exercise. Maybe if we get time, we will discuss about it. So, if we take some n number of integers, not necessarily all of them are distinct, call them a 1 etcetera a n, they are all coming from integers and not necessarily distinct. And if this is given, okay, the question is does there exist a subset of these numbers whose sum is a multiple of n. Okay. So, basically if this is what given, then prove that indeed we get actually the consecutive sums. So, there exists K L such that the summation A I ranging from K plus 1 to L is indeed a multiple of n. Okay. So, you look at this sum A k plus 1 plus etcetera plus A L. So, which is indeed multiple of n. In modulo congruence notation, we say that it is congruent to 0 modulo n. And this is basically an existence question, and given any n number of integers, you will be able to prove that always you have some consecutive sums that is actually a multiple of n, which is very interesting statement its own right, which can be proved using pigeonhole principle. Maybe we will discuss this later. Okay, I will stop here, and in the next class I would like to start with Mobius inversion, and maybe I want to state that result in somewhat generality. So, we will talk about partially ordered set and finite partially ordered sets. So, the Mobius inversion, which is true even for locally finite partially ordered sets, but we will just focus on finite partially ordered set and then prove the Mobius inversion formula. Okay, I will stop here. I will continue next time. Thanks.